Okay, good morning, good afternoon, everyone. Thank you for joining the IEEE EMBS webinar series on the frontiers of biomedical imaging and image analysis. My name is Kayhan Yan. I'm an associate professor of biomedical engineering at Rensselaer Polytechnic Institute. So our guest speaker today is Professor Kayhan Batmanghelich from University of Pittsburgh. He is actually joining Boston University in January 2023. So Professor Kayhan Batmanghelich is the assistant professor of Department of Biomedical Informatics and the Intelligent Systems program, and also with the secondary appointments in the electrical and computer engineering and the computer science department at the University of Pittsburgh. So he received his PhD from the University of Pennsylvania, UPenn, under the supervision of Professor Ben Tasker and Professor Krista Dabazikos. He spent also 3 years after that as a postdoc in the very famous computer science and artificial intelligence lab, CSL, at MIT, working with Professor Paulina Galland. So his research is at the intersection of medical vision, machine learning, and bioinformatics. So today he will speak about his research on bridging between AI models and medical insights, learning inference, and model explanation. So without further ado, let's welcome our speaker.
Thank you very much for inviting me. It's a great honor to be here. And good morning, good evening, or perhaps good night to people who are watching the presentation remotely. So today I'm going to talk about the research of my lab, where we try to view the insight that we gain from medical problems as a helper for our model development that help us through learning, statistical inference, and also model explanation. Hence, we view basically this model development and insight from medical domain as a bridge. And then you see also one of the most famous bridge called Andrew Warhol's bridge in Pittsburgh. So let's get started. Healthcare industry is arriving in a new era that AI is increasingly adopted by clinical workflow. One of the driving forces of such adoption is increasing the cost of healthcare expenditure. So this graph shows the cost of healthcare increased from 1970, even after correcting for inflation. It has experienced six-fold increase. Adoption of AI is going to have an impact for clinician and healthcare system by making them more efficient and also patient in terms of receiving personalized healthcare. So if we consider the application of machine learning in healthcare as a spectrum, that one side of that is bedside practice, the other end is medical research, ML has found application everywhere, from assisting radiologists by reading radiograph images faster to finding optimal embryo for IVF that reduce the chance of miscarriage, all the way to developing new drug. All of these amazing news that you hear about protein folding structure prediction that is a stepping stone in drug development. So throughout this spectrum, there are many challenges and of course opportunities for research for people like us. So I'm going to talk about 4 themes of the research throughout this spectrum that I think is the most important problem to address in my opinion. The first one is that decision making in healthcare is always multimodal. The doctors take a look into image of a patient, test notes, and the history of the patient in order to make a decision. How to develop an AI model that consumes all of these modalities of information in an efficient way is a challenge on its own. We are increasingly using more and more complicated model. We have to develop a model that is explainable, not only to gain a trust by the clinician, but also to audit our model to make sure that there is no underlying biases. Also, medical data are very expensive. How we can incorporate the domain knowledge in order to gain the data efficiency to take advantage of whatever data that we have. And finally, if we want to use this kind of data for medical research, we have to take this problem further away from just prediction, and we have to understand the underlying causal mechanism of the disease in order to contribute to the medical research. So my lab has contributed to many of these challenges. So today I'm going to talk about some of those. So from the point of view of application. So let me give you a couple of examples. So my lab has contributed to developing a model that jointly modeled genetic variation in the image and cognitive tests in order to identify a set of genetic variants that contribute to the Alzheimer's disease. And as a result, we can identify brain regions and genetic variants that are driving variation in those regions, and combine these two modalities. Also, there is a law. This is a stepping stone for developing new drug. Talking about new drug, there's a law called ERUM law that the number of new drug developed and approved by FDA per US $1 billion halves every 6 years, which is a bad news for drug development, means that it's becoming more expensive. One of the important steps throughout this process is to how to repurpose the new drug. So over the past few years, chemical engineers and machine learning practitioners have tried to develop a machine learning method that learns the underlying rules of these chemical grammars and make it searchable. So we have developed a method that combines this with the ontology of the drug that are already approved by the FDA in order to place a new drug in the ontology of the already approved drug. As a result, our method is able to identify secondary purpose for the approved drug in FDA, or the drug which is which may not pass all of the steps of the drug development. So, but today my talk is mostly about two aspects of the challenges of the healthcare that I mentioned earlier. The first challenge is to how we can gain a data efficiency using self-supervised learning. And the second one is about how we can incorporate that with multimodal data in order to gain efficiency, this time for statistical inference using the data that we usually discard. And the last part of my talk is about model explainability, which is one of the most important challenges in healthcare. So let's get started. So the first part of the talk is the work done with my former postdoc, Mingming Gang, and my collaborator, Kung Zhang, and two of my students, Kayhan and Li San. So what do I mean by weakly supervised learning? Of course, my wife say that when you are working, you're doing weakly supervised learning for my son. That's not what I mean today. But there are many examples of the weakly supervised learning. Sometimes the weakly supervised learning is taking advantage of the data that are overlooked or discarded, or sometimes can be using annotation that are easier to collect, less expensive to collect, or incorporating domain knowledge. And sometimes it's about bringing interaction to make the learning faster or data acquisition faster. But today, what I mean by weakly supervised learning, I'm going to talk about developing a method that requires less annotated data, and more specifically, bringing generalizability. One of the issues in the medical imaging domain and application of AI in healthcare is generalizability of the method that we have. For many of the problems, we either need to recollect a lot of annotated data that are very expensive. An example of that, for example, is COVID-19 that happens very recently, and there are a lot of interest on developing, for example, a method that we can identify COVID lesions. You probably have witnessed that while we are in the middle of the pandemic, our resource has to be allocated wisely. So perhaps if you want to develop a method that identify COVID lesions or identify the presence of the COVID symptom in the lung, we may not have enough data set. Also, many of the methods that we develop might be optimal for one symptom, but not for the other. For example, if you develop a method that is optimal for onset of the disease, might not be optimal for prediction of the hospitalization of the same disease, or predicting the chance of death for the same disease, meaning that every time that we want to develop a new features, we have to retrain a model, recollect the data. Now, the question is that, is there any way that we can learn a representation that is generalizable across multiple tasks? And one of the answers to that from the machine learning point of view is to develop a method so-called self-supervised learning that is not committed to one task, but alternatively learn a good representation that can be applied across multiple tasks. There are multiple different flavors of the self-supervised learning. Perhaps one of the most common one is contrastive loss. The general idea here is that, for example, if you want to develop a method that identifies there is a dog in an image without telling that it's a dog, you can apply set of transformation in an image that does not change the semantic. In this case, dogness of the dog is the semantic. And that constitutes a positive set. And a negative set is going to be set of random images that you collect from your data set. And then the contrastive loss try to find a representation that distinguishes these two sets from each other. Or in other words, find the features that the similarities among those variants of the dog are closer to each other, that we call positive set, than the one from pairs of a positive set and a negative set. So in the nomenclature of the self-supervised learning, the instance is called anchor, a variation of that is called positive set, and the random draw from your data set is called negative set. And there are one of the most common loss function for that purpose called info NCE is one of the most common ones. So now the question is that what would happen if you apply that naively on medical images? In medical images, the variation are quite subtle. For example, if you're collecting data set from the lung, all of these images are coming from the same context. But the amount of variation are very subtle. So what would happen if you apply that on medical images? So let's start with the some thought practice. We are extracting, let's say, some patches from images of the lung of the patient as an anchor, as a positive set, and we are going to extract set of the patches from the lung of the other patients from random locations. And we can use the same approach to extract that. What would happen? The issue is that if we apply this method unfortunately will learn how to cheat and use so-called shortcuts. To give you an example of the shortcuts, let's consider, just for sake of introducing the notion of shortcut, let's say that you are developing a method that is trying to identify there's a cow in an image. And most of the images of the cow are coming from the green background. So if you have a cow that's coming from some perhaps strange background, let's say seashore, the model will not identify it because it has learned to focus on a background. And this is what's happening if you apply this method naively on a medical images. Unfortunately, the notion of the shortcut are ubiquitous in medical imaging. So, for example, in this paper by Degrave et al., the authors showed that the deep learning approach that is trying to detect the presence of the COVID-19 from X-ray images focus on symbols of the hospitals or irrelevant or spurious information in order to identify in order to identify COVID-19 patient. So this is for supervised tasks. Self-supervised learning approach is no exception. In fact, even on the toy data set, we can show that such a method are quite vulnerable to shortcut learning. So let's assume that we want to, in this illustrative example, we have this toy data set that are coming from multiple symbols and with a different color and texture, and we want to learn in a self-supervised fashion all of these factors. For example, the starness, the shape, the color and texture. So if we hope that self-supervised learning learns all of these latent factors, it turns out that depends on the initialization of the method. The self-supervised learning may ignore some of these latent factors. we are hearing stating this theorem informally, but we also state the theorem formally in this paper that depends on initialization of this method. The self-supervised learning may ignore some of the underlying factors, and this is really bad for our application if we apply such a method naively. So in principle, to force the encoder to learn specific features, we should hold other features constant. For example, in this illustrative example that I'm showing above, the shape component is kept constant across the anchor and positive set, and also across the negative set. As a result, the model cannot use the shape as a contrast, and it has to learn the other factors in order to learn the distinguishing features between positive set and a negative set. So, but how can we do that? So what would be the equivalent of that in our application? In fact, if we show the images of the random patches to radiologists, one of the first things that they will tell you is this: oh, distinguishing positive set and negatives is very simple because we only need to look into anatomy. In fact, in this case, the anatomy will function as a shortcut. So how can we block the effect of anatomy if we know what the shortcut is, and in this case would be anatomy? How can we block it? It turned out that blocking anatomy as a shortcut is quite straightforward. If we construct our positive and negative sets that all of them are coming from the same anatomical location, we are effectively blocking this shortcut. And this can be easily done by using registration. So basically using image registration that aligns two images with each other to find a positive set in a smart way. So that will solve part of our problem. So the part of the problem that we were worrying that our encoder, instead of focusing on anatomical subtleties, focus on the anatomy that is not important for us. However, at the end of the day, we want to have a prediction as a patient at the patient level, not at that anatomical level. So how can we do that? Because every patient has his or her own anatomy. So to address that problem, we use graph neural network that the graph structures are built according to the graph to the anatomy of each patient, where the nodes are the patches and the edges represent the vicinity of anatomical location that is patient specific. And we use second level of the self-supervised learning in order to learn a patient level representation. So as a result, our method has two-level self-supervised learning. One that focuses on anatomical region and make sure that by image registration, we are blocking the shortcut. And the second level use graph neural network and adapt to anatomy of each patient and construct the patient level representation. I'm going to pause here to make sure that if there is any question, I can answer it. Please let me know if there is any question. If there is no question, I'll switch the gear and talk about the results. Is there any question?
So for audience, if you have any questions, just feel free to either type it in the chat window or raise your hand. We'll enable you to speak. So Kayhan, just a quick question. When you use the graph for the patient level learning,
Yeah.
do you actually learn like a different graph, a specific graph for each patient, or this just generated graph?
Yeah, because every patient has his or her own anatomical representation. So the graph representation for each individual difference are different. So that's basically our way of in order to make sure that we are adapting to patient specific anatomical variation.
Okay.
Yeah.
All right. I see actually two questions here. The first one from Hanqing Chao. Thank you, Dr. Kayhan. Can you please introduce a bit more about how the graph is formed?
Yeah.
How do you build the graph? Yeah.
Yeah. So the way that the graph is formed is as follows. Like we are in the first step, because we knew that there's a shortcut due to the registration, we perform registration to an atlas. So we have a coordinate system in each individual that maps to the atlas domain. And we have moving patches with some overlapping regions where the center of the patch are the nodes, and because of the registration, the patches have moved accordingly. And then we construct the edges between patches based on the percentage of the overlap between patches. Did I answer your question?
Okay, so another, yeah, he said yes. Another is to clarify, what do you mean by removing the shortcut of anatomy?
Yeah. So let me give you an example. So actually, let me show you this example. Do you see my slide right now?
Yes.
Okay. So basically, effectively, we have a positive set that are all coming from one patient, one location, with some augmentation like rotation or change in the contrast, etc. If we show this to any radiologist, if you show this to any radiologist, this is a positive set, and this is naive reconstructed negative set. In fact, the naively constructed negative set is randomly drawn from the population and location. If we show that to radiologists, radiologist says that all of the positive sets are coming from the same location, negative sets are from random location. It's very easy to construct a classifier, because effectively self-supervised learning constructed instance level classification. So as a result, the model will say, oh, that's a very easy feature, because the easy feature is to just learn the anatomy, and all of the positives are coming from the same anatomy, and I'm done. So, but an encoder that learns anatomy is not useful, because you're always like you're using only images of the lungs. We know the anatomy. What we want to see is the subtle changes on each anatomical location. So in this case, shortcut is a spurious features that basically prevents the model to learn a generalizable features. In this case, anatomy would be that easy feature. We want to prevent that. And image registration makes the negative set difficult, and as a result, make the task more generalizable. Did I answer your question?
Cool, thank you.
No problem. So can I continue?
Yes, please, thank you.
Okay, so let me talk about evaluation. So we trained the model on a large scale study of chronic obstructive pulmonary disease. And we are going to, and we perform a lot of evaluation. I'm going to give you the gist of evaluation in this slide. So the first level evaluation is that how does this method compares against a supervised approach? This is our method is self-supervised. Can we use how close that we can get to the supervised approach as some sort of like upper bound? The second method, which was initially motivate the development of this method, was generalizability. How generalizable these features are for the method that supervised method is not directly trained on. And finally, we are going to see what would happen if we change the disease. So here is a chronic obstructive pulmonary disease, which is one of the leading causes of death worldwide. What would happen if we change the disease to another disease, but the same modality, same type of images, in this case CT? Can we use this feature extraction on one disease and fine tune it to bootstrap another prediction of another disease, which has a smaller sample, in this case COVID-19? So let's get started. In the first part, we are going to compare our method with the supervised approach. So in this case, we are going to use two measures of respiratory, which are used for diagnosis of COPD. And one of those is called forced expiratory volume in 1 second, FEV1, where the patient is inhaling air and has to forcefully exhale forcefully exhale the air in her lung within 1 second. And if there is any obstruction or destruction of the tissue, the person is going to have a difficulty. So that is a metric of obstruction. And the second is the ratio of that to forced vital capacity. So we are going to use a supervised approach as an upper bound, because we train another supervised approach that use the lung imaging to predict these two metrics. So we want to see how much we can reach to this supervised approach because our self-supervised method are not directly trained on it. And we are going to compare our method with a couple of state-of-the-art method in self-supervised learning method in a medical imaging domain, for example, model genesis and other methods. So in this case, because the supervised approach is an upper bound, the closer the gap between self-supervised method and the self-supervised method and supervised method will be what we want. And we see that our method almost closed the gap to the zero, which basically suggests that by blocking the shortcut, you're learning generalizable features that performs almost as good as the supervised approach. So, but how generalizable this method is? One of the criticisms that I started this talk with was that, for example, if we train the method for FEV1, which is physiological metric of the COPD, the same features might not be generalizable for dyspnea, which is a functional metric of the shortness of the breath. It is still related to shortness of breath, and you do expect that the learned features are working very well, but in reality, supervised approach does not. So in this case, we are not going to, the supervised approach is no longer upper bound because it's not directly trained for that task, but we are using the pre-optimum layer of the supervised approach and retrained another shallow layers to predict so-called dyspnea score, which is modified, it's called MMRC, modified medical cancer metric of dyspnea, and another metric called centribular emphysema, which is a visual metrics of one of the subtype of emphysema. So in this case, the bigger the gap from the supervised approach suggests more generalizability. So the horizontal line is a supervised approach, and we want to see how much we can increase the gap. There are two take-home messages from this. First of all, most of the self-supervised approach surpass the supervised method in terms of generalizability. Our method gives bigger gap. We're suggesting that by the way that we construct our features, by blocking the shortcuts and constructing patient-level representation, we can even provide more generalizable feature. So, which address the first problem that we were talking about, that we can learn and we can construct the features that are generalizable across multiple different of the severity of the disease for one disease. But the next level would be that how generalizable this approach would be for completely different disease, but the same type of imaging. So in this case, we are going to see how generalizable these features are for COVID-19, which is coming from the same anatomy, lung, and the same modality, CT images. But here the goal is that we only have a small sample size, only 1,100 samples from COVID-19 of the 3D CT. And we want to see whether this approach that is trained on COPD, chronic obstructive pulmonary disease, can bootstrap this method. The data set is coming from Moscow Department of Health. There are 5 levels of severity that is decided based on clinical measures such as oxygen level, temperature, and heart rate, as well as reading from the CT. And here are the gist of the results. So the take-home message is as follows. Due to small sample size, if you train a supervised method, it's going to overfit, does not perform very well. In fact, 3 of the self-supervised method, they're all going to outperform, that are trained on COPD gene, which is much larger sample size, and adapted to COVID-19, going to outperform the supervised task. The last 3 bars are 3 variants of our method, where in each bar we are turning on and off one of the features of the method. For example, blocking the shortcut, the way that we are constructing patient-level representation. And we see that in each, by turning on and off each of the properties of the model that is specifically designed by insight from the domain, we can increase the performance of the method and bootstrap a small sample size. So we had 2 aims at the beginning of the talk. One was that how can we construct features that are generalizable, that can be applied across multiple domain, across multiple diseases, for multiple metrics of the same disease, etc. But the question is that is this imaging endophenotype or imaging representation that we have learned can help us in order to understand the underlying causes of the disease, or so-called etiology of the disease. So we have constructed new patient-level representation. How is it related, or if it is related, to underlying causes of the disease? And in order to do that, we have to relate what we see in the images to other modalities of the data. So the question that we are interested in this case would be that this new phenotype, these new self-supervised features, high-dimensional features that we have extracted and summarized images with, and we are claiming that is as generalizable, is it related to underlying causes of the disease? To be more specific, in our case, we want to answer this question. Is the destruction of the tissue that we see in CT images are related to involvement of the immune system that we can measure using, for example, blood samples? And we know from the previous work that percentage of emphysema, which is very simple imaging metric extracted, are related to involvement of the immune system. What we want to see is that that's very simple imaging features. The way that we construct the new features is using quite complicated procedure. Is the signal still preserved? And in order to answer the question that how is it related, before that we have to answer this question, if it is related or not. We have two modalities. One modality is that is imaging features that we are using, for example, self-supervised approach to summarize it to some high-dimensional representation. And we have other modalities, samples that are coming from the blood, specifically for inflammatory response of the disease. And we want to see if they are related or not. Before answering the question of if they are related, how they are related, we have to answer this question that if they are related. Formally speaking, questions like these are usually formulated as hypothesis testing, where the null hypothesis is that these two modalities are independent from each other. And we want to see how much evidence we can collect to reject this null hypothesis. That would be the first step before understanding the relationship. So the power of tests like this is usually governed by the number of the patients that have both modalities. Patients that are coming with a CT scan and they have their blood work. However, I'm sure many of you that are working with such a data have experienced something like this, that you have a lot of patients, you have a set of patients with both modalities, but we have way more patients that only have imaging data, but not blood work, and a lot of patients that have only blood work, but not imaging data. This is what we call unpaired data because the other pairing modality is missing. And I'm sure many of us would have asked that I wish there was a way that we can exploit this data because this is the data set that is usually discarded. This is also a common problem in industry, which supported part of this research. They are also interested in how can we take advantage of the data, expensive data that we collect that we usually discard. So in the following slide, I'm going to give you the general idea, how can we take advantage of this data set, this unpaired data set we usually discard. So the general idea is as follows. We are trying to reject the null hypothesis that two modalities are independent. Mathematically speaking, the joint distribution under the null hypothesis can be written as a multiplication of the marginals. The very least that unpaired data can help us is to provide a better estimate of the marginals, which means that by providing better estimate of the marginals, we can improve our estimate of tested statistic under null hypothesis, and as a result, we can improve the type 1 errors, false positive. And that's the very least that unpaired data can help us. So let me give you a little bit of detail. We have extended the method called Hilbert-Schmidt independent criterion proposed by Gretton et al., where the finite sample estimator of the test statistic almost looks like this. I'm saying almost because there are some ugly term that is proportional to the cubic term of the n, and I remove those from this slide to avoid the visual clutter, but the test statistic roughly looks like this, where the K is the kernel for X modality, in this case imaging, that is a patient-patient similarity. We can compute this using patient representation using self-supervised approach that I told you earlier. And similarly, L is the kernel for Y modality, in this case, blood test. And H is just a constant matrix. It's called centering matrix. So if we view K and L as matrices, where each and rows are patients, the solid color in red and green represent the patient that have both modalities, and the dash color represent the remaining patient that either have only blood work or only have imaging. So it turned out that you can rewrite the test statistic as the eigenvalues of these big matrices, and unpaired data set can help us to provide a better estimate of this eigenvalue, and as a result, better estimate of the type 1 error. We also further studied this problem theoretically. We showed formally in this paper that type 1 error, which is about false positive, reduces as you have more and more unpaired data set. This is the informal statement that you see here. The formal statement is in paper that basically the gist of that is like this. The estimator that we designed that take advantage of unpaired data set become more and more accurate as you provide more unpaired data set. The second theorem says basically says that if you are willing to assume that data is leaving some low dimensional manifold, which is, by the way, the case about many of the real data set, we can even improve the power to compared to an independent test that does not take advantage of the unpaired data set. So this is an informal statement of the theorem. The formal statement are in the paper. So in the interest of time, we perform a lot of experiments with this. They're all in the paper. In the interest of time, I'm going to be very brief about the experiment. So on a simulated data, we studied two scenarios. In the first scenario, two modalities are basically irrelevant from each other. In this case, the null hypothesis is correct. So we are going to look into false positive. And the second scenario, two modalities are relevant to each other. And in this case, and they're following some low dimensional assumption, in this case, the null hypothesis should be rejected. As a result, we are going to power up the test. So let's start with the first scenario. So this is a typical example of the method that I mentioned earlier. On the x-axis, we are showing the number of unpaired data set added to the data. And on the y-axis, you see the type 1 error. The blue line represents the method that does not take advantage of the unpaired data set. And as a result, by adding more unpaired data set, the behavior of that does not change. The horizontal line on the top, the dashed line, is represent the nominal level that we typically use to reject the null hypothesis, typically 5%. So as a result, you see that the unpaired data set does not change the behavior because the unpaired data, as you add more unpaired data set, it gets discarded, so it stays the same. We have two variants of our method. I didn't go through the detail of that. It's just like different ways of deriving the test statistic. They're both of them. As you add more unpaired data set, they hover around the predefined value. The take-home message of this figure is as follows. The take-home message is that by adding more unpaired data set, the type 1 error does not explode. A bad method basically, as you add more unpaired data set, may surpass the 5% nominal value that we use for rejecting the null hypothesis by a lot. But this method is well controlled, meaning that by adding more unpaired data set, you can have a good control. One variant is more conservative, the other variant is more aggressive. But they're all hovering around that nominal 5% that we want our false positive to be. Under the assumption that modalities are related to each other, we have to look into the power. Again, y-axis is the power. X-axis is the number of unpaired data that we are adding to the model. The blue line represents the method that does not take advantage of unpaired data set. As a result, their power stays the same no matter how many unpaired data set you add. And the best that you can possibly achieve is that a person reveals the data set that's missing to you. So, oh, this is the data. That's the best that you can achieve. That's called oracle, basically upper bound. And the two variants of our method fill the gap between naive approach that is wasteful and the oracle that's best that you can achieve and improve the power. So going back to real world application that we were interested in we are interested in this question. Is the destruction of the tissue that we see in CT images related to involvement of the immune system? This has been hypothesized and addressed using only one-dimensional imaging features in the paper in one paper that I showed a couple of slides ago. But we are constructing much richer features, and we want to see if this connection is still preserved. So as a result, because we know that null hypothesis in this case should be rejected, we have to look into minus log p-value of the null hypothesis. The blue line shows the result, but unfortunately, we only have very small number of patients that have the blood work, but a lot of them have CT images. So we use this method, and we added more unpaired data set. The blue line shows that if we don't take advantage of unpaired data set, you cannot reject the null hypothesis, although you know that the immune system is involved. By adding more unpaired data set, by enough unpaired data set, you eventually reach the level that the null hypothesis has to be rejected. So let me give you a sneak peek of what we are going to do with this new imaging phenotype. As I mentioned earlier, COPD is a highly heterogeneous disease, and our goal is to define a phenotype for the disease. So given the new features that we have constructed, and is highly general and informative across multiple metrics of the disease severity, can we relate this to, for example, transcriptomics gene expression and define a new axis of the disease? By new axis means that the new direction that characterizes the progression of the disease. And here I'm showing you the result only on 2 dimensions for sake of better and easier visualization. So here the absolute value is not important. Each dot is one patient. But as the value of these 2 axes, on x-axis and y-axis increasing, the severity of the disease are increasing. Each dot, as I said, is one patient, and the color represents the traditional spirometry value. The darker the color, the worse is the performance of the patient during the spirometry measures. So let me show you some prototypical performance of the patient here. So here are examples of the CT images, coronal view, and the red color represent emphysema regions. So these cases on the right, you see a lot of emphysema. The one on the bottom, there are a lot of red. There are a lot of emphysematous region in the lung of this patient. In the lung of the other patient, the patient is not doing well, but the amount of emphysema is still relatively large. On the other patient that you see on the left panel, this patient is doing pretty bad, but there's not much of the emphysema in his lung. So it shows that emphysema on its own is not sufficient. When in fact, when we look at the properties of the patient, BMI of the patient, the way that the patient performed during the walking, and show it to our collaborator who's pulmonologist, he said, I don't know this term, I'm quoting from him, that I don't know if this term is still used in medical school, but this looks like a two prototypical patient that we usually called pink puffer. So the pink puffer are the people that are basically defined, they usually tend to be thinner, and they tend to be older patient, and they have very severe shortness of the breath. And we see a lot of hypertension in this individual, and they're called pink puffer because their skin tend to be pink. The second subgroup that I showed on the right panel, what they refer to as a blue blower. These are the individual that tends to be a little bit more obese and has a lot of sputum, but this subtype of emphysema is usually defined based on appearance of the patient. While we discovered this subtype by connecting CT characteristic and relating back to the gene expression of the patient. As a result, we can dig in deeper into underlying etiology of the disease. So let me summarize the first part of my talk. The first part of the talk was about our first aim. How can we incorporate the specific context of the domain that are essential for method development in order to block the shortcut, block learning spurious features, and constructing features that are generalizable and can be used to characterize multiple aspects of the disease simultaneously. We also show that such an approach can gain data efficiency by going through by transferring the problem to another domain, another disease, although same anatomy, same data modality, and bootstrap small sample data set. In the second part of the talk, I try to switch gear and talk about data efficiency, not in learning, but in statistical inference. We showed that when we are constructing high-dimensional representation, high-dimensional phenotype, performing a statistical test become more challenging, and as a result, we have to be more frugal in terms of the data that we are wasting. So we develop a method that uses the data set that we typically get rid of, that we call here unpaired data set, and we show that under some we can provide a better control of the false positive, and also under some assumption we can even gain power. So that summarizes the first part of my talk. If there is any question, I'm happy to answer. Otherwise, I'm going to switch gear and talk about explainability.
So that's a great point. So my question, you discussed the unpaired data set. So that you have X and Y, and any X generalized work. Say we have three things, and X, Y, Z. You do not have all of them measured. So this will be a generalized scenario. Any work along that direction?
Yeah, that's a very good question. So let me tell you a little bit of backstory at why we started this. As I mentioned in one of the slides, at the end of the day, we were interested in understanding the causal relationship. But before answering causal relationship, we have to answer correlation question. And we started with a simpler problem of pairwise correlation, where each modalities are high dimensional in this case. So when you have three examples or more, like the problem becomes even more difficult because there are multiple scenarios that you can think of. Of course, one way that you can address this is that you can concatenate any two pairs of the scenario, use the same method. That will answer still correlation question. But if you are interested in answering causal question, for example, let's say I have X, Y, and Z is a confounder. And in this case, I'm not only interested in correlation because I know that confounder is related, but I want to see how it's related. I want to learn the structure of the graph between these three random variables. You can use pairwise relationship, in this case, pairwise testing. This is basically what we develop is pairwise testing as a building block to learn causal graph. And there are many of my colleagues, Kun Zhang, who's pioneers causal graph learning, has used this pairwise test to learn a causal graph. I have to say that learning causal graph is much harder problem because before going toward deploying a method for causal learning using pairwise tests that take advantage of unpaired data set or any other method, the identifiability is much harder problem than just learning the structure. And we did not touch that in this paper.
Do you think pairwise relationships are sufficient to determine the structure, or you think you need a higher order studies?
Well, to learn the structure of the graph, let's say that we are not, for a second, we are not worried about identifiability issue. And I'm assuming that we have enough sample that we are also not worrying about multiple hypothesis testing. So this is like a lot of the big assumption. You can use pairwise correlation of pairwise nonlinear correlation in this case between samples to construct to basically discover the structure of the graph, assuming that you don't have a factors of three orders. So factor of three orders, like for example, if I have in the language of probabilistic graphical model, if I have a phi that is function of X, Y, and Z all at the same time, I'm not sure the pairwise connection can discover that. But
yeah, you answered my question. Thank you.
No problem. Any other questions?
Okay, another questions here.
Sure.
So people actually studying the multi-modality information, they often use the CCA, canonical correlation analysis. So how they also can extend that to like using the deep learning extract features and do the CCA. They call it deep CCA. So how's your approach related to that? What's the main like a difference advantages?
Yeah. So in this case, we were focusing only answering this statistical question that like if these two modalities are related to each other or not. One can develop a statistical test based on CCA, although I don't know how the null distribution, I'm sure it has worked out, but I don't have it on top of my head that like how this null hypothesis distribution would be under CCA. You probably need to make some assumption that how the distributions of each of these X and Y's are, and then develop a null hypothesis. So this is from developing test statistic point of view. There are kernel version of the CCA which are related to HSeq. Also, CCA can be viewed as a regression, and I think that would be the connection. That's the best that I can answer, that one can view CCA as a regression, except that a regression that reduced the dimensionality before doing that. There is a paper by Vunu et al. In 2012 in NeuroImage that viewed basically CCA as a low rank dimensionality reduction formulated as a regression. I recommend people looking at it. That would be the closest connection. And then as soon as you constructed the regression, you can make it kernelized and then derive all of this machinery. But that's the closest connection I can think of.
Okay. All right. Thank you.
No problem. So can I go to the next part of the talk?
Yeah, absolutely. Thank you.
So the next part of the talk is about model explainability. So model explainability is very important in the context of application of the AI in healthcare, not only to gain a trust by clinicians, but also to audit the model to make sure that it's not focusing on spurious features. So this is the work that is done by my graduate students, my former graduate student, Sumedha Singla, and my collaborators in radiology department, Stephen Wallace, and my former postdoc, Brian Pollock, and my wonderful collaborator, Motahar Islami, who help us a lot in order to take the explainability one step further by not only explaining the model, but also thinking how the interface of such a model would be with the human, because her expertise is in human-computer interface. Motahar is a faculty in human-computer interface department in CMU. So perhaps one of the most common approaches for model explanation in computer vision are model attribution, saliency maps, such as GradCam, etc. So let's say that you train a classifier that tells you there's a cat or dog in an image. A saliency maps basically identifies set of pixels in the image that are most relevant to the output of the classifier. So such an approach basically answer you where question. However, application of such a method for medical imaging is quite problematic. It sometimes results in poor localization. In this case, we are talking about a nodule supposed to be very localized, but you see that the GradCam produce very diffuse result. In some other cases, different diseases result in more or less same location anatomy that renders the understanding of this GradCam approach for explaining the output of the black box to the doctors very difficult. In fact, every time that we showed our result to our radiology collaborator, we always come back that, oh, get this heat map off the image. I want to see what's in the image. And he always come back with the same question. What should change in the image so that the deep learning produce in a different output? So what he said made us think deeper about the whole notion of explanation. In fact, he was more interested in why question rather than where question. That is, where question is typically answered by the GradCam, but he was interested in why question. So philosophically speaking, this is what contrastive or counterfactual explanation is. So we came up with this idea that, so let's say that we have a classifier, in this case F, that we call it black box, that whenever we input an image, it produces some sort of a factual output, and which is the probability of a certain disease. So we call it factual output. So what if we can view the output as a knob so that our radiology collaborator, he can play with this knob and move it, let's say by delta, and ask what should change in the image that creates this counterfactual outcome. So, and then the goal of our explainer function that here represented by the green box is to generate another image, and such that if we plug in back to the same black box, it creates that desirable outcome or that counterfactual outcome. So as if this knob can exaggerate or de-exaggerate the effect of the disease and show it manifested itself in the image. So such an explainer can be viewed as a function that is a function of input image X, the black box F, and the delta amount of the movement of this knob. So we thought about this as what would be the criteria that this function should satisfy. It should produce an image that looks realistic because we need to convey that to the radiologist, including presence of the support devices, etc. Because the radiologists want to make sure that the identity of the patient is preserved. It's about the same patient. It should be also compatible with black box, in this case, F function, or neural network, which means that if we change the knob and create an image for explanation and plug the image back into the black box, it should produce the desirable output according to the position of the knob. And it should be also self-consistent, meaning that if I bring the knob backward and get the original, I should be able to get the original image. So in the following slide, so I'm not going through the detail of the way that we constructed. Effectively, each of these criteria can result into a loss function. The details are in this paper, and we use a generative model, more specifically conditional GAN, to construct this approach, except that we provide this knob. There are quite a bit of detail, but let me talk about the results, the way that we evaluate it. So we evaluated for the sake of visualizing whether this model works. For the people who may not be familiar with the X-ray imaging on a toy data set and visualizing the X-ray data set. But this is just visual explanation. How would we evaluate this quantitatively would be the basically gist of this work. So let me show you some visualization to just have an idea how this method works. So let's say that for sake of example and and tell you how this knob will operate, consider that we have a classifier that distinguishes a person in the image is smiling or not. So in a person in the first row, is by playing this knob, we are basically exaggerating the effect of smiling in that person on the top, from one end of the spectrum, which is not smiling, all the way to the other end of the spectrum, and other way around for the other case. So this is just showing you, visualizing on a very easy to understand example that how this operates on a toy data set. So this is an example of that applying on so-called cardiomegaly, which is abnormal enlargement of the heart. And you see that by playing with this knob from one end of the spectrum to other end of the spectrum, it results in change in the size of the heart. Similarly, for pleural effusion, the hallmark of the pleural effusion is that at the corner of the lung that is supposed to be sharp, if there is a pleural effusion, it becomes so-called blunt. It becomes like a curvy shaped structure. So if you look at the corner of the lung, you see that from one corner of from one end of the spectrum to other end of the spectrum, this sharpness of the corner is introduced, meaning that our explanation is focusing on something that is as expected clinically as a definition of the disease. So what about like keeping identity? We designed the loss function in a way that, but this paper is accepted. I forgot to change the title at the bottom, is that it preserved some of the important support devices in the lung. So it's the patient, the image on the top is the real image, and you see that like the pacemaker is preserved, because this was quite distracting for our clinical collaborator. They want to make sure that we are not changing the identity of the patient. We are not jumping from one patient to another, and this method is able to preserve that. But these are all qualitative. I'm going to show you some the quantitative way that we can evaluate our counterfactual. The first criteria would be that we design, we have multiple criteria that such an approach has to satisfy. We are going to see how much it satisfies the criteria to design it for. In a second set of experiment, we are going to validate our result against the clinical rules that are used for diagnosis of the disease. For example, if it's a cardiomegaly, it should focus on the heart because it's about enlargement of the heart. If it's about pleural effusion, the blunting effect at the corner of the lung should show up. And finally, because we need to communicate that with human, we are going to design a set of experiments that see how much it can communicate, how effective it is in terms of communicating with human, basically human-computer interface of such explanation. So if you remember this figure that I showed you a couple of slides ago, one of the criteria was consistency with the black box. For 3 different diseases, cardiomegaly, pleural effusion, edema, we showed 2 axes. On the x-axis, we see the expected value of the counterfactual, basically how much this delta changes, the value that we expect the output of the counterfactually generated output would be after the plugging the image into the black box. And the y-axis, sorry, that's the y-axis, and the x-axis is the desired axis. If the model is consistent with the black box, they should, regardless of where the patient start more like healthy looking or abnormal looking, they should follow the 45-degree. And for 3 of these conditions, they're all more or less follow the 45 degrees. Each of these curves represent the starting point of the patient. For example, the darker the image means that the patient more like healthy looking, and the brighter the color means more abnormal looking. And regardless of where they start, it follows this 45-degree. As an external metric of evaluation, we use the clinical definition of the cardiomegaly to see how consistent our explanation is with the clinical definition of the disease. So for cardiomegaly, we look into so-called cardiothoracic ratio, which is the ratio of the heart to the lung. So we synthesize the image, we apply image segmentation to segment the heart and lung, and computed the CTR ratio, and computed how much is counterfactually intervention in an image change the CTR and how the statistical significance of that. So as a result, we are looking to delta CTR, meaning that initially the patient has some CTR value if we apply the segmentation of the heart and lung, and then if you go to other end of the spectrum, the CTR value should change. And as a result, if the patient looks normal, the CTR should reduce, and other way around if the patient looks abnormal. And we see that our method introduced such a change in a CTR value in a statistically significant way. For pleural effusion, the hallmark of the pleural effusion is this blunting effect at the corner of the lung. So we train a detector to count the number of times that you see this blunting effect on the images. We apply this counterfactual generated image. So if the image is normal, you should see more blunting on a population level. And we see that the counterfactual generated image increase the level of this blunting effect that we see on the image, and reduce that if the patient looks abnormal, and this is statistically significant. Now, the next level of that would be how helpful this method is for conveying the biases for the doctors, how helpful it is, how much the clinician agree with the explanation. I won't go through the detail of that. The detail of that is in this paper that is going to appear in MedIA. We basically ran a survey. We designed an interface. We ran a survey with 12 radiologists, and we asked them first to diagnose the image without showing explanation, and we showed different kind of explanation without telling what that explanation is, and see, do they find it helpful? How do they change? How do they agree with the decision of the classifier? The details are in the paper. And we compare our method with saliency map, cycle GAN, and our approach. And the example of the saliency GAN are like maps like this. The cycle GAN, we create an animation, but except that the cycle GAN can only go to 2 ends of the spectrum. For our method is able to create both saliency map and also this animation. And we showed that to radiologists and asked the questionnaire. So long story short, in terms of understandability, we show that such an approach that allows this level of interaction for radiologists substantially improves the understandability of the black box for the radiologist, and compared to other methods, which is here represented by blue box, and also much more helpful in terms of helping during the basically pipeline of the process, in terms of like trusting the method and then using it for downstream task. I won't, the detail of the design are quite elaborate, and in the interest of time, I won't be able to go through the detail of that. But 57% of the participant, random participant, find this way of interacting much more helpful. So let me give you a peek into ongoing research that, okay, let's say that you explain the black box. What is that? How can you use it? Unfortunately, there is not much time to dive into this like application of this method, but let me give you the gist of it. So I'm going to borrow some terminology from causal inference literature. So our method basically allows us to intervene in an image, which is indirectly intervening in activation of internal neuron inside of the black box. So if we map the pattern of activation to the medical concept available in radiology report, we can use tools from causal inference, for example, so-called mediation analysis, that identify a set of neurons that mediate the output, and basically in this way open the black box and provide the explanation that is closer to the language of radiologists. So as a result, we are able to construct to approximate the decision of the black box into a set of neurons that makes the decision making similar to the way that the radiologists make a decision. For example, we can say that there are a set of neurons that focus on pleural fluid, and if that pleural fluid is false, there is a set of another neurons that are focusing on vascular prominence, and if it is false, then it's normal. Otherwise, there are other set of neurons that are focusing on other clinical terms. So this is effectively going one step further and opening the black box of the black box and explaining the terminology that is more close to the language of the clinicians. And then what else can we do with this model? By intervening in the neurons that are responsible for undesirable properties, for example, biases, we can fix the black box. Effectively, we can put an explainer and black box in a self loop to fix undesirable properties. In this paper that is shown below, we use the explainer to fix undesirable properties of the black box, in this case, overconfidence black box, and fine-tune it accordingly. So in interest of time, I won't be able to go through the detail, but let me summarize the last part of my talk. We develop a method for counterfactual explanation that provide a knob that increase or decrease the effect of the abnormality and effectively exaggerate of the level of abnormality. And the results are consistent with the clinical definition of the disease. We also perform human-computer interface survey that shows how helpful this method is in clinical decision making. As a work in progress, we are connecting explainability to the causal analysis field, and that will open a whole set of possibilities that we are quite excited about. We showed some high-level example in our Mikai paper last year. And we can also use such an approach to fix undesirable properties of the black box model by fine-tuning. On that note, I would like to thank the really hardworking members of my group that basically did all of the heavy lifting for this work, and my wonderful collaborators that made this research grounded and always gave us their insight, help us to develop a new approach. And of course, funding institution that make this from NIH and NSF and industry that made this research possible. Thank you.
Thank you, Kayhan. Excellent talk. Yeah, that's wonderful. Thank you so much. Now we can actually open to the audience for questions.
So this is a great approach. I mean, your counterfactual approach. And I notice you have a explanation function. You introduce natural changes to explain the prediction.
That's
And
right.
my question is, do you think there would be a possibility, and there are some natural change that also explain the result? For example, you look at heart, different ratio, but the same thing, I could not change heart, but rather I introduce fatty liver, so some liver property will also give you same explanation. So any comments on that possibility?
That's a very good point. It's possible that, so there are two things. One, let's say that like there are, so let's say we are to focus on cardiomegaly and you introduce some changes that these changes are not related to the heart. Let's say only change the intensity level because all of the patient with the cardiomegaly coming from different scanner, and you see basically change in the overall intensity that is basically model focusing on shortcuts. Now the question is that, is this the effect of the model focusing on a shortcut or explainer focusing on the shortcuts? Do you see what I'm saying?
Mm.
So let's say there are other contributors to the disease that are not biological. Let's say that there is always marker on the image that says that this patient is coming from hospital ABC, and hospital ABC is only admitting patient with cardiomegaly. Let's say that shows up in the counterfactual image.
Mm.
So now the question is that, is counterfactual explainer focusing on those features, or it's actually model is focusing on those features? So because that's the whole, if the model is focusing on those features, then explainer is useful because it's basically showing the underlying biases. Right? It's showing that because the whole purpose of creating this explainer was that we want to audit the model. We want to see that if it's focusing on good features or bad features, the spurious features. I think in that sense, I believe that explainability approaches are not ready for auditing yet. And that's my opinion.
Okay. Okay. Thank you.
And yeah, so we need something a little bit more than that to make sure that there is a visual explanation, and we want to ensure that we basically want some sort of a guarantee that if we are, let's say, seeing some spurious features, we have to provide a guarantee that it's not coming from explainer, it's coming from black box. Because if there is a bad property that black box is focusing on, we want to know, and that's why we are providing. We are working on explainability, but I'm not sure the explainability method, including ours, still ready for full auditing the models yet.
Thank you.
No problem.
Okay, thank you. Kayhan, I have one more question regarding that training the counterfactual model. So that reminds me the sharp model. They also have some counterfactual factors there to change to see what's the effect on the kind of a result as the explainability. So here, so how do you train that model, the generator model? Do you need actually those images that kind of label to supervise that?
So this is basically the general architecture of that model, roughly speaking. And this is like our older version, the newer version is slightly different, but roughly the idea is like this. You have a black box F, and you have an encoder that creates some coding of the input image. And then there's a generator that not only accepts the code, but also accept the knob value. So you can basically provide any value of the knob that you want. It creates a new image and you plug it back. So there is no labeling needed, because the delta is given by the training procedure, and as long as it's consistent with, if you plug it back and then produce delta difference, then you're good. So you don't need new data.
I see. Okay.
And if you set, and then also in order to make sure it's consistent, if you set the delta, you can set the delta to minus, so you can pass the generated image to encoder again and set it to minus delta. And then it should produce the same image.
Okay.
So no
Cool.
more data, no more labeling is required.
That's great. Excellent. Thank you.
No problem.
I guess because of time, we can conclude session here. Although actually, while it's very interesting research, we still actually have a lot of questions, but we can actually read the papers, get to know more details there. Yeah, with that, we probably conclude the session here. Thank you again. Thank you to our speaker.
Thank you for inviting me.
Talk.
Thank you. It was a great honor.
Right. Keep in touch. Thank you.
Yeah, of course. Thank you very much.